I'm Jancy Despain with Bright Idea Tutoring. In my NMR series, I'm going to teach you the skills that you need to take a molecular formula and an NMR spectrum and turn it into an accurate structural formula. Now, there are a lot of videos online that teach you the NMR theory that you need to know, but my focus here is really going to be on the skills and the process of interpreting the NMR spectrum. So my hope, though, is that by watching me do these processes over and over, you're going to pick up a lot of the skills and a lot of the theory that you need. So if you have questions, hit me up in the comments. I'm going to be referencing some data that you'll need, and you're going to find links to all that data in the comments section. So let's just dive right in. And you may notice that this first spectrum is going to be pretty easy, but just bear with me because what I'm going to teach you here is going to prepare you for a more difficult one that we're going to do next. Whenever you see an NMR spectrum and a molecular formula, the first thing that you're going to want to do is just figure out the double bond equivalence in that molecular formula, because that's going to give you a lot of information about the compound. Now, you may already have a formula for double bond equivalence that you know from before or that came with your book. And if you're comfortable with that, then just use it and ignore me for a second. But if you don't have a formula that you've already got memorized, I've got one that's really easy to use. And here's that formula. We're going to use the number of hydrogens predicted by this standard alkane formula, CnH2n plus 2. And all we got to do is look at the number of carbons and predict how many hydrogens should go with that number of carbons. So we've got 7 carbons. 2 times 7 is 14, plus 2 is 16. So that's 16 hydrogens predicted by that formula. Again, based on 7 carbons. So 16. Now we're going to look at our actual number of hydrogens. That's 6. And if there were any halogens, we'd add 1 for each halogen. If there were any nitrogens, we'd subtract 1 for each nitrogen. We're going to ignore oxygens. We just pretend like they're not even there. So we've got 6. We're not adding or removing any. So we subtract 6 for the actual number. And we divide by 2. 16 minus 6 is 10, divided by 2 is 5. 5 double bond equivalents, or elements of unsaturation. That lets us know that there are 5 double bonds, or rings, or some combination of those with triple bonds in our compound. The reason why that's important is, first of all, if you have 4 or more double bond equivalents combined with 6 or more carbons, that's almost a guarantee that you've got benzene in your compound. So we're going to be looking specifically for benzene when we go to look at our NMR. Also, 4 double bonds would be tied up in benzene, or 4 double bond equivalents. And we've got 1 more. So we're going to be thinking, where else might that double bond show up? So now we've taken care of this, 5 double bond equivalents. Let's take a look at what other information we can get from our molecular formula. We've got 1 oxygen. What functional groups might be there? 1 oxygen could be an alcohol, an ether, or an aldehyde. Those are our options. So let's think about what we might expect to see in our NMR spectrum. An alcohol usually gives us a broad singlet. And that broad singlet, in my experience, can kind of show up anywhere. A lot of charts that you see can show that broad singlet in a certain range. I've just kind of learned that it can be anywhere in the whole spectrum. I'm just going to specifically look for that broad singlet, and it usually looks a little bit wider and shorter. Now an ether is going to have sp3 carbons next to an O. And usually 1 or both of those carbons are going to have hydrogens, protons on them. And because those carbons are next to an O, they're going to show up somewhere in the 3 to 4 range. So I would expect to see a signal in the 3 to 4 range. And it could be higher or lower depending on what else is around. Now, if we had an aldehyde, aldehyde signals show up as a singlet in the 9 to 10 range. So I'm going to be looking for these specific signals to tell me what functional group this O is a part of. And I'm also going to be looking for benzene signals in the 7 to 8 range. Benzene almost always shows up between 7 and 8 to confirm for me that these 4 of the 5 elements of unsaturation, or double bond equivalents, are indeed benzene. Now, before we start looking at all of these numbers, because I know I just want to dive right in there, let's also look at our integrations, which seriously, we don't even need to do for this compound. This is so easy, but let's cover all our bases. These integration peaks, or integration lines, show me how many protons made each of these signals. Now, sometimes you're just going to see these written out as, 1 hydrogen and 5 hydrogens to tell you how many protons made each signal. But sometimes you're going to be given them in this form, and you're going to have to identify for yourself how many protons made that signal. And the easiest way to do that is just to get a little piece of scratch paper. Okay, so I always measure the smallest one first, and I just assume that that smaller one counts as 1 proton. So here's 1 proton. I'm going to assume that that's 1. Then this would be 1, 2, 3, 4. I could approximate that that's 5. I'm not 100% sure about that. So a good way to confirm is to say, all right, in this spectrum, I see a total of 1 plus 5 is 6 protons, and there are 6 protons in my molecular formula. So yes, that makes sense. So I can feel good about this now. It also makes sense that there would be 5 protons on a benzene ring that had 1 substituent, and there would be 1 proton on an aldehyde group. So if I were going to draw this, there are 1, 2, 3, 4, 5 protons on a benzene ring and 1 proton on my aldehyde group. So I have a mono-substituted benzene. This is benzaldehyde. And if you want to look in the comments, I'll have a link to benzaldehyde, and you can actually see its true NMR spectrum, which obviously looks quite a bit like this. But it's always good to see a real spectrum and see what the truth looks like versus my unskilled drawing. Now that we've looked at that first, more simple spectrum, we can analyze one that's a little bit more difficult. And we'll just use the same method. First, we need to look at the molecular formula and see how many double bond equivalents, or elements of unsaturation, it has. First, the number of hydrogens predicted by this formula. It's based on the number of carbons. 8 carbons times 2 is 16, plus 2 is 18. So there are 18 hydrogens predicted. And then the actual number of hydrogens is 8. There are no nitrogens or halogens to change that number, so we're just going to leave it 8. 18 minus 8 is 10, divided by 2 is 5. Again, if there are 4 or more double bond equivalents, that would make us suspect that benzene is present. And of course, there have to be enough carbons in our molecule to make benzene an option. And since we have 6 or more carbons and 4 or more double bond equivalents, we're going to guess that benzene might be present. So I'm going to go ahead and write that here. Maybe we've got benzene. We just need to look in the 7 to 8 region of our spectrum to confirm that benzene is there. I also want to check my molecular formula to see what other functional groups might be present. Whenever we see 2 O's, an O2, we want to think, could there be a carboxylic acid or an ester? And for both of those, carboxylic acid or an ester, we're going to need an extra double bond equivalent, which we have. If we potentially assigned 4 of these to benzene, then there is 1 extra one that we could assign to a carboxylic acid or an ester. So if I wanted to look for these in my NMR spectrum, I would look for the carboxylic acid proton in the 10 to 13 range. And finding an ester in an NMR spectrum is a little bit tricky. Where we would look for that is the protons on this carbon tend to show up around 2.1, And of course, they can shift one way or the other. The protons on this carbon tend to show up, I would say around 3 to 4, but I just look in that general area. Whenever we see two O's, we don't just want to consider that they are together in one functional group. We also want to consider that they might be in two separate functional groups. So we also need to look at the possibility of an aldehyde, an ether, or an alcohol. And like we discussed before, aldehydes show up around 9 to 10, ethers show up around 3 to 4, and alcohols show up as a broad singlet. And that broad singlet can really be anywhere in the spectrum. Now, before I go all out and start analyzing my spectrum, I do want to figure out my integrations. That means I need a piece of scrap paper. This one's already been used, but I'm going to use a different side of it now. I'm going to call my smallest one 1. So here's 1. That makes this 1, 2, 3, Is it 3 or 4? I call that 1. And then I'm going to call this 1, 2, that looks more like 3. So, how do I know how to handle this? Well, 1 plus 3 plus 3 is 7, or 1 plus 3 plus 4 is 8. I have a total of 8 protons in my structure, so I need to go with 8. So that means this needs to be 4. So even when there's some uncertainty in our measurement, we can use logic to figure out what is the right answer. All right, now let's look at our chemical shift. We've got something between 9 and 10. That points to our aldehyde. And that's really helpful because if we have a proton tied up in an aldehyde, that means one of our O's is in an aldehyde functional group. That means one of our O's has to be in one of these other functional groups. You can't have 2 O's in an ester if one of them's in an aldehyde. And you can't have 2 O's in a carboxylic acid if one of them's in an aldehyde. So we already know we don't have either one of these groups. Besides, we don't have anything in the 10 to 13 range. Sometimes they'll actually extend your graph to show something out here, or sometimes they'll show a little offset to show you that there is something off the charts. But in this case, we don't see anything like that, so we know we don't have this. Now let's look what else we have. 7 to 8, that's benzene. And we have a signal at 4. That's our ether. I don't see a broad singlet anywhere, so we know we don't have an alcohol. So I'm pretty confident now that we do have an aldehyde, we do have an ether, and we do have benzene. So I can go ahead and put benzene here. That takes care of C6H what? Well, there are 4 protons on benzene. So that's going to be C6H4. Where do we want to put those protons? Whenever we have 5 protons integration in our benzene area, that's easy for us because 5 protons on benzene means that there's 5 H's and 1 substituent. So it doesn't matter where we put that substituent. But when we have 4 protons in our benzene integration, that means we have 4 H's and 2 substituents. And a disubstituted benzene can be ortho, meta, or para. And we can tell whether our benzene is ortho, meta, or para just by the shape of this signal between 7 and 8. Ortho tends to just be a messy signal. I've heard professors liken it to cut grass. The reason why an ortho signal looks like this, let's say these are 2 substituents, is because these 4 protons all have similar chemical shifts, and they're all going to lump in together. A meta signal tends to be the cut grass with a singlet in it. Now the singlet can be right in the middle of the cut grass, or it can be off to one side on the right or on the left. And where that comes from is here are our meta substituents. These 3 protons cause the cut grass appearance. They're all similar chemical shift, and they all kind of get right on top of each other. This one, though, is a singlet, and it causes the one singlet, whether it's right in the middle or off to the side. Now, with para-substituents, you're going to get a doublet-doublet pattern, 2 doublets. And that's caused by these protons and these protons. These cause a doublet and these cause a doublet. And you can see right here that we have a doublet-doublet pattern. So we know that our 4 protons are here and here. We've got one substituent on this side and one substituent para to it. Now we've got to figure out what these 2 substituents are. We know we have an aldehyde group, so we could kind of guess that there might be an aldehyde group here. But what if that aldehyde group is at the end of a chain? Like, what if there's a CH2 here? We don't know, right? But check this out. 3 protons made this signal. That's probably a CH3. Almost any time you see an integration of 3, you probably have a CH3, a methyl group, making that signal. This would make a 2 proton integration. And we don't have a 2 proton integration anywhere on this graph. So we can pretty much know that there's no CH or CH2 here. What we've got to have is a CH3 on this side. Now, are we done? We've got another O to account for. And we also have to account for the fact that this has a chemical shift of 4. And remember when we looked at our functional groups, we said that that chemical shift of 4 made it likely that there was an ether functional group. These protons are likely next to something highly electronegative. That's why we can guess that our O is right here. So I'm going to attach my aldehyde group to this side and my oxy group, my methoxy group, to this side. This compound is para-methoxybenzaldehyde. And if you want to look in the comments below, I'll attach a link to look at a real NMR spectrum of this structure. I do also want to mention, see how there's a little bump in this integration pattern. That bump happens because these guys made an integration of 2, and then these guys made an integration of 2. And normally, if you see a bump like that, you should count these 2 integrations separately. You should say, well, that's a 2, and it goes with this signal. And that's a 2, and it goes with this signal. And the reason why I didn't do that here is because we know that all of this belongs to benzene, and so we're just going to treat it all as one signal. But if this had been in another part of the spectrum, we would have counted those 2 separately and treated them as 2 separate signals. And I will handle something like that in another video, so just stay tuned.